Okay, so welcome everyone. This is the 13th, I believe, week of Üçgen. And today we have Oğuz Şavk from Boğaziçi University. He is a third-year PhD student, and he's going to talk about Brieskorn spheres, homology cobordism, and homology balls.
Thanks for having me. Today, I am gonna give very near algebraic geometry talk. I hope that everyone enjoys, and please feel free to ask questions. Let's first investigate our main question. For this, we need two definitions. A closed-oriented three-dimensional manifold Y is called integral homology sphere if it has the same integral homology of three-dimensional sphere. And we may similarly define integral homology ball. Since the standard three-sphere bounds four ball, we may ask the homological analog of this question. What it is, which integral homology spheres bound integral homology balls. Actually, it is a very important problem in low-dimensional topology, and it appears in the famous problem list of Kirby. First of all, Friedman completely answered this question in the topological category, and he proved that every integral homology sphere bounds a topological integral homology ball. So we need to update our question to the smooth category and asks which integral homology spheres bound smooth integral homology balls. In this case, this question is more subtle, and there are both positive and negative answers. To get positive answers, you need to follow constructive methods such as Kirby calculus. On the other hand, there are obstruction methods. In this site, you need to compute invariance of homology spheres. Today, we're gonna discuss in both directions. At this point, this question is really interesting for me. I try to motivate you more by relating two important concepts in low-dimensional topology, such as embeddings and cobordisms. First of all, we know that every integral homology sphere smoothly embeds in five-dimensional sphere. This result is due to Hirsch, Rahlin, and Wall independently around 1960s. So we want to make the target space smaller, so we ask which integral homology spheres embed in S4. Again, Friedman gives the complete answer, and he proved that every integral homology sphere topologically embeds in S4. Actually, Friedman classified closed simply connected manifolds in the topological category. So his result even implies Poincare conjecture in dimension 4. These theorems of Friedman's are actually just corollaries of his main theorem. So again, we add an extra smoothness condition and says which integral homology spheres smoothly embed in S4. And it is another important problem in Kirby's list, and we have a very easy fact from algebraic topology, and we know if we have an integral homology sphere which can be embedded in S4, then it splits S4 into two integral homology balls. And the consequence of this fact, this embedding implies bounding homology balls. And this fact can be seen from the Mayer-Vietoris sequence. The other concept is homology cobordism. Also, we can form a group structure on the set of integral homology spheres by modding out two of them if they co-bound an integral homology sphere. So we are talking about a group structure. Its operation is induced by connected sum of manifolds. Here the identity of the group is homology cobordism class of three-dimensional sphere, and we can find inverse elements by taking the orientation reversal. I have two remarks on the definition of integral homology cobordism group. First of all, here, if you erase the homology condition on W, you get a trivial group because Rahlin proved that every integral homology sphere bounds a compact smooth four manifold. On the other hand, again, due to Friedman, smoothness condition on the four manifold W is necessary. If you drop this condition, you get a trivial group. So we define very sensitive group object by starting with low dimensional manifolds. This fact can be seen from the definition of homology cobordism group and says that an integral homology sphere bounds an integral homology ball if and only if it is homology cobordant to three-dimensional sphere, because three-dimensional sphere behaves as a trivial element in the homology cobordism group. So we have three notions. This is an overview, and an integral homology sphere smoothly in S4, then this sphere bounds a smooth integral homology ball. In this case, it is homology cobordant to three-dimensional sphere. How about the reverse direction for the first implication? Actually, it is an open problem in low-dimensional topology. All well-known examples can be embedded in S4 or homotopy S4. Then this question is related to smooth Poincare conjecture in dimension 4, which is the last Poincare conjecture. Today, our main objects will be Brieskorn spheres. Given pairwise coprime integers, the Brieskorn spheres can be defined. They are very special class of three manifolds, and their roots lies in algebraic geometry. Before defining Brieskorn spheres, I talk about two important characterizations. First of all, Brieskorn spheres are different than a three-dimensional sphere because their fundamental group are not trivial. On the other hand, they are always integral homology sphere. We can imagine Brieskorn spheres as in the picture here. Black sphere describes five-dimensional sphere. The red cone gives us the variety, and the intersection describes the green Brieskorn sphere. Actually, it is a model for a famous Poincare homology sphere, which is Brieskorn sphere sigma 235. Now, I give the mathematical definition of Brieskorn sphere. We can rewrite actually a five-dimensional sphere in complex coordinates. And now we consider a holomorphic function f defined by the rule x to the p plus y to the q plus z to the r. Then the zero set of this function is defined by VF. This variety also so-called complex hypersurface. Clearly, our function has an isolated critical point at the origin, and we want to focus the structure of the variety close to the origin. And to do this, we intersect our variety with the five-dimensional sphere. This is the length of the singularity at the origin and actually gives us Brieskorn sphere. And Brieskorn spheres are three manifolds. Here, the dimension calculation is actually subtle. I tried to write it explicitly yesterday. I need two important and classical theorems from differential topology. We define the function f from a three-dimensional complex space to one-dimensional complex space. Then pre-image theorem says that this variety is a complex surface, complex two-dimensional manifold, so that it is a four-dimensional real manifold. Transversality theorem also explains the transverse intersection of manifolds. They describe the codimension, so we easily found that codimension of the Brieskorn sphere is 3. These objects are all inside six-dimensional real space, so that the dimension of the Brieskorn sphere is 3. Any questions so far?
No questions from me.
All right. We can realize Brieskorn spheres as the boundaries of Plumb 4 manifolds, and this is the plumbing graph. We can find these integers by solving this type of equation, and this solution, to find the solution is fairly easy, because as you see, we can take mod p, q, and r reduction and find the other integers. To finding integer weights in the graph explicitly, we compute continued fractions, and it is also not a hard job. In the language of algebraic geometry, these plumbing graphs corresponds to minimal resolution graph of Brieskorn singularities.
That's cool.
This is the fourth part, and it is about Kirby calculus and construction side. First of all, Kirby calculus is introduced by Kirby in 1979. Actually, it gives complete moves which relating four manifolds. You may heard Raida-Master moves for nuts. So Kirby's work corresponds to some type of link moves for four-dimensional manifolds. And then our main question now is which Brieskorn spheres bound integral homology balls. We know that lots of integral homology sphere bounds integral homology balls, and these all works are from around 1980s, following the Kirby's article. Now, we say that bounding integral ball implies bounding rational ball. Again, it is an easy corollary from algebraic topology. So we may wonder the reverse direction, and this motivates the following definition. We say integral homology sphere non-trivially bounds rational ball. So it is some kind of weak question if it does not bound an integral ball. So we are looking for integral homology spheres bounding rational balls, but not integral balls. And so this is the question. Also, we can rewrite this question in algebraic framework in terms of homology cobordism group. And actually, this question corresponds to finding non-trivial elements in the kernel from integral to rational homology cobordism group. Why this is true? As I said, we are looking for integral homology spheres bounding rational balls, so that these spheres will be trivial in the right-hand side object. And we want that they also do not bound integral balls, so they will represent non-trivial elements in the kernel. The first example is obtained by Fintuchel and Citon in 1984, and actually they show that the Brieskorn sphere sigma 237 non-trivially bounds a rational ball. So their result can be interpreted as this natural map is not one-to-one. Furthermore, we can show that this kernel contains an infinite integer subgroup. Actually, we generate this subgroup by the Brieskorn sphere 237. It depends on the connected sum behavior of Neumann-Ziebenmann invariant, and also requires that we have to know that Neumann-Ziebenmann invariant is an invariant for homologic spheres. This result also due to Savalier. So the second corollary is depends on the work of Savalier. And this algebraic, at this point, we just know that kernel contains this subgroup, and we think that it is much more larger, but it is again an open question. Before describing the new methods, I need to describe dent surgery on nuts. Consider a nut K and its exterior nuts are circle embeddings in the three-dimensional sphere. So exterior means we remove tubular neighborhood of the nut from three-dimensional sphere. These neighborhoods are always solid torus. So on the boundary of this solid torus, we always find a curve which bounds a disk. And the boundary of solid torus actually classical torus, so that we can rewrite this curve gamma as a linear combination of meridian and longitude. What is the surgery tree manifold? Surgery tree manifold can be obtained by gluing the tubular neighborhood of nut to the nut exterior by respecting the following homomorphism hash. So the surgery manifold can be understood from this continued ratio PQ. The recent progress is started by the observation of Akbulut, Selman Akbulut and Kai Larsen, and here Y denote the three-dimensional manifold obtained by zero surgery on figure 8 nut, as you see. They observed that any integral homology sphere obtained by integral surgery on Y bounds a rational wall. What it means, if you do one more surgery on any nut in the three manifold Y, again, you get a closed oriented three manifold. They say that if it is further integral homology sphere, then it must bound an integral, it must bound a rational homology ball. And using this observation, they presented the first additional examples after Fintuchel-Citon, and they show that the following Brieskorn spheres non-trivially bound rational homology balls. Actually, you may see that the Brieskorn sphere sigma 237, which is the example of Fintuchel-Citon, has remained single example for more than 30 years, so that the technique of Akbulut and Larsen very important and very influential. I followed their work and technique and found new infinite examples actually show that these Brieskorn spheres also non-trivially bound rational homology balls. Now, I described the proof for the first family. Actually, it is fairly same with the second one. On the left side, you see the surgery diagram associated our Brieskorn spheres, and the right one describes the additional -1 surgery. And this is the base case, n equal to 1 case, our proof. As you see, we always blow down -1 components so that we reach the 3D manifold Y. How about the general case? And we first of all, again, blow down -1 dark black component. As you see in the second picture, there is a -2 chain together with -1, so that if you blow down n-1 times, you get the third picture. But the third picture was also appeared in the base case, so you may follow the same flow, and you get that by using, of course, by using the lemma of Åkerlund and Larsen, you get that our Brieskorn spheres all bound rational balls. I don't write here explicitly, but again, the obstruction comes from Neumann-Zibelman invariant. For even ends, our Brieskorn spheres do not bound integral homology balls, but for odd ends, we have no idea. And all well-known current integral homology cobordism invariant vanish for our spheres. So it is again an open question. If you prove that our Brieskorn spheres are linearly independent by using some kind of homology cobordism invariants, you will conclude that the kernel contains the infinity subgroup. I also reprove the classical results as I did mention before, but here the conclusion is Brieskorn spheres bounding integral balls. So here we do not use the technique of Åkerlund and Larsen directly, so that I manipulate their technique, and for these Brieskorn spheres, I reprove this result by starting with unknot or Steve-Dorn knot. This is also related to algebraic geometry. I call Wn Ramanujan Plumb 4 manifolds. Their boundaries are always again integral homology spheres, and they all bound integral homology balls. Why I called Ramanujan manifold? Because the n equal to 1 case, base case, is appeared in the classical article of Ramanujan. It was written in 1971 before Kirby calculus. Actually, W1 is the first example of a contractible complex surface which is not isomorphic to a complex plane as an algebraic variety. Ramanujan's result also exhibits the first exotic algebraic structure on the three-dimensional complex space. Actually, this is interesting, but I don't know the general four manifolds here are whether are complex surface or not. The last part is about the invariant Hegardt-Fuller homology and obstructions, and this is joint work with my PhD advisor Çağrı Karakurt. In this part, we focus on the algebraic structure of integral homology cobordism group. Actually, it is very complicated. Recently, Dai, Holmes, Stoffregen, and Turong show that this group has a Z-infinity summand. Here, Z-infinity summand means you direct some integers with itself countably infinite many times. So you are looking for kind of linear independent family of cobordism invariants. And interesting point is that these results are always obtained by analyzing homology cobordism invariant of Brieskorn spheres. Now I highlight the recent theorem of Dijkhoff, Stoffregen, and Turong. They actually show that the Brieskorn spheres sigma 2n plus 1, 4n plus 1, 4n plus 3 generate infinite rank summand. And this Brieskorn singularity actually are the boundary of this plumbing graph. Of course, their result is due to construction of new three-manifold invariants, as I said, but there is also computation side. You need to compute some previous and new invariants. First of all, you need to compute Oğuz-Szabo D invariant and want that this type of invariants are arbitrarily large for your spheres. The second stage is the computation of some special part of Hegardt-Fleur homology. And the last step, of course, is the computation of new cobordism invariants coming from invertive Hegardt-Fleur homology. Then this is the expected question, and can we find another families of Brieskorn spheres generating the infinity summands independently, and can we generalize also this singularity by keeping the above three Fleur theoretical invariants same? The answers are both yes. Actually, they are in the same package. Now PQ and R denote the pairwise coprime integers satisfying the identity PQ plus PR minus QR equal to 1, then the Brieskorn spheres is the boundary of such a nice plumbing graph. We call such manifolds almost simple linear graphs, because if you omit the edge, including minus P vertex, you just get a linear graph and all vertices are minus 2. There are lots of solutions of this identity. First of all, the famous Poincare homology sphere. The second singularity is also very interesting because there is a classical result in low-dimensional topology says that every three-manifold can be obtained surgery on links. So we may naturally ask that can we realize all three-manifold surgery on nuts? The answers are very far from yes. The second singularity is the first infinite family of three manifolds which cannot be obtained surgery on nuts. This is the result of Hom, Karakurt, and Lidman. The third family, as you recognize, the first family generating the infinitesimals, fourth, fifth, as I count correctly, I don't know. Yes, fourth, fifth, and seventh are new. The singularity P plus 1, P squared plus P minus 1 can be obtained minus 1 surgery on torus nuts P plus 1. The last singularity also very interesting. It comes from Fibonacci numbers and very complicated invariants. Actually here, the first triplet, again, Poincare homology sphere. And Hegardt-Fleur homology, as well as D invariant, is introduced by Peter Oswald and Zoltan Szabo in the beginning of the millennium. And then these invariants and the corresponding homology can be used answering lots of questions in the low-dimensional topology. Why this invariant is important, why we care about. Because first of all, it recovers famous diagonalization theorem of Donaldson. The second is about they provide the D invariant provides homology cobordism invariants. Also, we can use this invariant also not concordance invariant, because if you take a knot and then its double cover is just a 3 manifold, so you can treat the invariant also not invariant. The Oğuz-Szabo algorithm runs on the very special subset of second cohomology of the 4 manifold X. They are called characteristic classes, and they include all information in the second cohomology. Actually, they are related intersection forms. I don't want to go into details of Oğuz-Szabo algorithm because it is very technical. Here, I just present its flow. You start with an initial class K, and then running the algorithm, you generate a full path which includes a bunch of characteristic classes. At the last step of the algorithm, you decide your full path is good or bad by looking at the terminal class. Here, the set C denotes terminal characteristic classes supporting good full paths. As you expect, we eliminate lots of redundant elements in the algorithm so that this set is strictly smaller than the set of characteristic classes. Oğuz and Szabo says that it is enough to compute the invariant on this smaller set. And here, K square means the multiplication of the transpose of characteristic vectors are just tuples. So you think them as matrices. Here, K square can be obtained by K transpose inverse intersection matrix and K. Actually gives you just an integer. So the invariant for plumped manifolds is just depending on finding the maximum of K square. What we do, what is our proof strategy? We first of all determine terminal classes of above simple linear graphs. It is easy. It is fairly easy because if you are looking at Oğuz-Szabo algorithm, you easily see that bootful paths never include 2 vertices which are -2. The second step is the same analysis for almost simple linear graphs. Of course, it is related to our first observation. You need to find K squares. You compute entries of inverse intersection matrices. It is generally very hard, and but in this case, it is fairly simple. We use the method of Nemeth and Nicolaescu.
Also, what is intersection matrix?
Intersection matrix is associated to 4-dimensional manifolds, and they can be defined by the cup product. And to write intersection matrix, you need to analyze cup products of second cohomology. I mean, entries are pairs coming from second cohomology, and the outcome is just integer.
Thank you.
Together with Karakurt, we first proved that for even integers p, the invariant is equal to QR plus Q plus R over 4. Actually, this theorem is not depending on the previous analysis, because as you see, if P is even, then all vertices are even, and which means your Brieskorn spheres bound even intersection form. In this case, zero characteristic class maximizes the K square, so that K square is also zero, and D invariant is just the number of plumbing graph, the number of vertices of plumbing graph over 4. But the odd case is very complicated and gives a rich result, and of course depends on the previous analysis. And for an odd P, we obtain such a formula for K square. Here, A and M lattice points, integer pairs, only depending on the integer P. For example, these are lattice points for the triplet 11, 12, 131. There are 5 lattice points. You need to, if you want to compute the invariant exactly, you find the lattice point which gives the maximum. So also the lattice point 1, 1 always in our set, so taking the maximum makes sense. Also, these lattice points gives lower bound on the D invariant of such Brieskorn spheres. Actually, that is our, again, main theorem. For an odd P, this is the D invariant. We don't get a closed formula for this case, but actually, at least we know that D invariant is D invariant is greater or equal to P minus 1, which is a non-zero integer. As I said, D invariant is the cobordism invariant, so that we obtain such an obstruction and conclude that our Brieskorn spheres never bound rational balls, so that never bound integral balls. These pretzel knots are not rationally sliced, so that they are not actually smoothly sliced. Here, rationally sliced means your knot bounds a disk in a rational ball. The classical smoothly sliced means is a same kind of characterization, and your knot bounds a smooth disk in a 4 ball. So smoothly slicedness implies rationally slicedness. What we get this obstruction, because if you assume that these pretzel knots are rationally sliced, as I said before, their double branch covers gives these Brieskorn spheres so that they bound a rational ball. This is a obvious contradiction. The integral conclusion here and smoothly slicedness are from very old result of Fintushal and Citern. Actually, I remember the date is 1985. We find exact values of the invariants by specializing certain subfamilies, and of course, we analyze their lattice points. As you see, the lattice point 1, 1 gives the maximum for the invariant of several Brieskorn spheres, but this is not the case in general, so that we cannot find a closed formula for the D invariant. But if you know the triplet, it is somehow easy. In an upcoming course, we will compute also their connected Hegardt-Fleur homology introduced recently by Holm, Hendricks, and Littmann, and we will prove that these Brieskorn spheres also generate the infinitesimal in the homology cobordism group. You may wonder that this Brieskorn spheres are independent from the first family or not. For even n, we know that these first and second family are not homology coordinate to family of Dihom, Stoffregen, and Turong. Actually, the third family is independent from all of them. And today, that is all I want to say. Thanks for your attention.
Thank you, Oğuz. Thank Oğuz with either uploading or by reactions in the chat, or both if you want. Any questions or comments for Oğuz today? I am curious about one thing, if anybody is still thinking about some questions. Why did it take almost 30 years, or more than 30 years, for people to come up with these families of examples? Is it because nobody thought about them, or because it was too difficult?
It is too difficult, actually, and it is somehow, it is not somehow, it is directly related to handle the composition of four manifolds. And if you have a Brieskorn sphere or general and integral homology sphere, which bounds rational ball but not integral ball, then its handle decomposition must contain three handles. And actually, we don't know how to draw three handles. This creates a problem. Also, the second issue is the lack of the technique, and Akbulut and Larsen provides somehow a simple and easily understandable technique.
Okay. Any more questions? Comments? If not,
I have one. This in the last theorem, this Z infinity.
Yes.
Parts, they all come from direct, like just connected some of these things with each other. Or each one of them is just one part of.
Each one of them, actually, they are not coordinate to each other, so that J generates the infinity summand.
Okay. Like a part of one element of direct sum just corresponds to one n.
And if you take one element from this family, let's say n equal to 1,
yes.
Then the connected sum of these Brieskorn spheres generate just Z
okay.
summand.
Okay, okay. That was my question.
Any other questions?
And like another question, maybe.
Yes.
Like, is there something some expectancy on this about this group? About what can be known? I don't know.
Actually,
maybe
this
like,
group.
Maybe is there like finite element things?
This is a great question, and we don't know integral homology cobordism contains torsion group.
Okay.
And we do not expect any torsion in the integral homology cobordism group. Another interesting question would be says that if you think Brieskorn spheres as subgroup of the homology cobordism group, and you may ask that Brieskorn spheres generate the whole group or not. And actually today, some people give negative answer for this question.
Oh.
And this is, of course, sad result, because all we know comes from Brieskorn spheres.
By today, you mean this day?
Yes, this day. They put a preprint on archive.
Okay.
Today or yesterday, I'm not sure. At least yesterday.
Okay. Not like a general today.
Yeah.
Okay, any more questions?
I have a question. Considering the motivation you gave at the very beginning, so then you introduced these spheres, Brieskorn spheres.
Yes.
And I wanted to ask, like, what is the motivation to use Brieskorn spheres, like, or say, what is the motivation intersecting sphere with the singular surface, like specifically that variety? Are there other type of approaches which, you know, use other type of varieties intersecting and then, I don't know.
Brieskorn singularities are very interesting. Actually, they can be defined in any dimension. For example, in 7 dimension, Brieskorn singularities gives the exotic spheres due to Milnor. And in the 3 dimension, you can get integral homology spheres by surging knots or by taking some kind of general 3 manifolds, for example, cipher fibered spaces. And here, the interesting point for me is that they are always homology sphere and they are different up to homeomorphism, but homology cobordism here is a weaker relation than homeomorphism, and they are at this level also complicated. So maybe we need to we need to create weaker notion than homology cobordism and analyze this type of 3 manifolds.
Thank you.
I have another quick short question. Which geometry out of 8 geometry in 3 dimensions, which ones is like these Brieskorn spheres belong? If like do they belong one of them or several of them? Are they spherical?
They lie in the 6 geometries of Thurston's 8 geometry. Okay. They are almost all of them.
Okay, thank you.
But geometrical classification is somehow is not essential, because even in standard torus, you may see lots of curvatures. So we need to classify 3 manifolds in terms of some topological notions. And of course, we need to reprove Poincare conjecture.
Any more comments, questions, thoughts? If not, let's thank again to Oğuz.
Thanks for all questions.
And usually at this point, Turkish stops recording